Okay, hello students. We're back again for to this course, chapter 3, part 4, which is optical components. Let's quickly look at the components used for optical fiber communication system. Okay, without much ado, let's begin. First of all, we look at the light sources. What are the components that provide the optical light for optical transmission? Number one is the laser. You know, we talk about laser and LED. These are the two highly used optical components that we use to generate the light source in optical fiber communication. So these two are, the first one is actually called the diode laser. It's not just called DL. It's not just called laser. It's called diode laser. And then the second one is the high radiance light emitting diode, LED. So these are the two sources of light that is fed into the optical fiber system. Is that okay? So the first aspect, what we're looking at, is the source of light into the optical fiber cables. The sources of light, where the light comes from. They're coming from the diode laser and the light, very high radiance light emitting diode, LED. So the diode laser is preferred source for medium to high data transmission. Except you're doing low one, you're not doing the, you're doing just low data transmission. That's when you use the LED for the source of light. But if you want the medium to high data transmission rate, then you have to use the diode laser for the generating the light pulses into the optical fiber system. Okay, now let's move on to the next thing. Another thing is the technology that is developed to synchronize the light through the optical fiber system. This technology is dense wavelength division multiplexing. The dense wavelength division multiplexing. Okay, please take note. The dense wavelength division multiplexing. What this means is that we have so many in this in the first chamber, the first aspect of this channel. You have so many signal inputs here, which will be coerced into one channel to pass through one channel, and then we get the multiplex output where you have the modulator side of it. Yeah, the beginning is the modulator side of it, and then everything goes through one channel, and then you get the output where the signals are brought out as demodulated values. And then this technology that synchronizes with light, with optical fiber transmission, is called the dense wavelength division multiplexing. So this is the second source of what we are supposed to look at, because first we say the source of light, where the light is coming from, which we said whereby we say the diode laser, which is the commonly used one for medium to high data transmission rate, and we say the light emitting diodes are only used for low data transmission rate. So the commonly used one, which are for high data transmission rate and medium data transmission rate, are the diode laser. So after looking at the source of light, we're looking at the technology that synchronizes this light and enables this light to move through. Now this technology is called the dense wavelength division multiplexing. Okay, so all the light impulses that are going into this channel will be multiplexed to pass through one channel. So this technology that helps to multiplex these lights, so many rays of light, into one strong one, it's called the DWDM, which is the dense wavelength division multiplexing. Okay, most lasers emit a fixed wavelength, but there is a class of lasers called the tunable lasers, in which the fundamental wavelength can be shifted to a few nanometers. So most lasers, they work with a fixed wavelength, but however, we have what we call the tunable wavelength or tunable lasers that can work with different fundamentals of wavelength. Tunable lasers that can work with different wavelength, and these ones have more nanometers in their distance. So these ones are able to work exactly with this technology. Now, if you look at the market, the primary market for this device in the network operation environment, where we use this our technology, the dense wavelength division multiplexing, or where this type of technology is being used, the traffic routing is often made by wavelength. The traffic route is as a result of what wavelength does the impulses of the light they have, and as such, wavelength and transmitter must be assigned and reassigned to accommodate dynamic routing, and networking, so that we will have, at the end of the day, we have an increased bandwidth or a bandwidth on demand, and a seamless restoration and serviceability optical packet switching, and all of these good things will be the result of the day. All of this improved capability will be the result of the day. So what we are saying in effect is that for this dense wavelength division multiplexing, it has enabled these advantages. It has enabled these advantages. It accommodates dynamic routing. It accommodates dynamic routing. This technology accommodates dynamic routing, and it increases or improves our networking capability and ability, and it also enhances our bandwidth, and it also has an ability to restore if there is a signal failure, ability to auto restore the system, and also has improved optical packet switching ability. So this technology is second to none. Now let's move quickly to a subhead. Another thing we're supposed to learn in optical fiber component called the splicing. Okay, remember this chapter, it's about optical fiber components. This chapter is optical fiber components. We've talked about the light source as component. We talked about the technology used. Now we're talking about splicing. Splicing is just a way of joining two optical fiber together. Okay, the way of joining two optical fiber together. Optical fiber is made of ultra pure glass, right? They're made up of very pure glass. Now, optical fiber makes window glass seems opaque by comparison. Your normal window in your house, it looks opaque. Opaque means something like something that light cannot go through. So the window in your house, the way optical fiber glass are so pure, if you compare them with the windows in your house, it makes the windows in your house look opaque. That's what we're saying. It makes the window, by comparison, if you compare there, it seems as if the windows in your house are opaque. Light cannot go through. So optical fibers are super pure. They are ultra pure substances made of ultra pure glasses. Is that okay? Windows made of this pure glass 1 kilometer thick would be as transparent as normal pane of glass. It is therefore not surprising that the process of making connections from light source to fiber or from fiber to fiber, the light source is where the light is coming from, like your laser, the diode laser, to the fiber itself, or from fiber to fiber if you splice them. You know, splicing is joining two fiber together. We're going to talk about the method for splicing. Okay, if you splice them, you can you say from fiber to fiber, and also from fiber to your detector, from fiber to, so there are three-phase algorithm that we're talking now, three-phase system we're talking about, the source to fiber, fiber to fiber, and fiber to detector, and all of this becomes critical in our system. So we must take a holistic look at this three-phase in order to have a perfect system that works without mismatch, because losses are coming from result of a mismatch in your splicing methodology. When you splice optical fiber cable, if they are not properly spliced or they are not properly laced together, then there will be losses resulting from mismatch as a result of mismatch coming from your spliced optical fiber cable. Now remember, I said splicing is just joining two optical fiber cables together. Now the low loss capability of the glass fiber can be severely compromised if the connections are not accomplished in exact fashion. What this means is that if you do not align or splice the two optical fiber together accurately and appropriately, there will be a lot of losses coming from the result of errors of what you've done. Now let's take a look at this. Furthermore, we say optical fiber are joined either in a permanent fusion splice or with a connector. Either we use a connector to join optical fibers together, or we use what we call the permanent fusion splice. A good example of permanent fusion splice is when we use mechanical method. Mechanical means to join optical fibers together. Okay, remember we have the fusion method and we have the mechanical method. We're going to talk about these two methods of joining optical or splicing. Okay, now let's move on. The connectors allow repeated mating and omitting. So if you connect it well, it will mate properly, and then there will be low loss. And if you don't, there will be a lot of loss in the system. So as technicians or as administrator, you must be able to learn. You should learn how to splice optical fiber accurately. Above all, these connections must lose at least little light, right? There is nothing that is perfect. It doesn't mean when you splice two optical fiber cable or two optical fiber wires, there will be no single loss. No, there will be, but we are saying it should be as low as possible, because if there's too much loss, then we should have gone for the twisted pair cabling. Now, no loss depends on the correct alignment. You must align these wires accurately as possible, of the core of one fiber to the core of the other fiber, the core of this fiber A to the core of fiber B. I'm going to show fibers why they should be aligned correctly and accurately to reduce loss in the fiber. Okay, if they are not properly or perfectly aligned, then there will be to the connector, within the connector there will be a lot of loss. Now let's take a look at this. Look at this. This is let's assume this is one optical fiber cable, this is another optical fiber cable. What you see here is that there is an axial misalignment. The axes are not exactly, the core of this cable is not aligned to the core of this optical fiber cable. So there's an axial misalignment. There will be a lot of loss here. If you transmit along here, so many will fall out here from here, because they are not aligned properly and accurately. So there's an axial misalignment that taking place here. Now here you have, in this place you have an angular misalignment. There's a gap here. There's an angular gap here. So when you transmit data through this optical fiber, some of them will drop out of this place. They will not. There's an angular misalignment here. So there will be a lot of huge loss here when you misalign this, when you splice very wrongly. Now here there's air gap misalignment. So here also loss can occur, although there are air gap in mechanical alignment. Well, there are air gap in mechanical alignment, because mechanical alignment is different from fusion alignment. Now let's go to this third one, the deeper, the rough surface misalignment. So there's error here due to rough surface. Then there's what we call numerical aperture differences. If you look at this the aperture of this and this, they are not equal. The angle here and the angle here, they are not the same. The angle in this first place is like 90 degree, while the angle here is like 60 degree, so or less. So there is a mismatch. So this mismatch is called numerical aperture difference. Okay, then this one super core size differences. The core size here, this one, the core size is super small compared to this one. This one is bigger. There's core size misalignment here. Then here we have the core concentricity offset or offset. The concentricity, they are offset. They are not put together exactly in a concentric manner. Here we have the core ellipticity here. There is an elliptical misalignment of the core of these two optical fiber. So all this type of misalignment causes loss in the fiber cable. Now let's move on quickly. Fusion splicing. There are two types of splicing in optical fiber cabling. I've already mentioned that. The first one is called the fusion splicing. Now let's quickly, the second one is called mechanical splicing. Now let's quickly talk about the first one, which is the fusion splicing. Okay, when we talk about fusion splicing, connectorization as splicing, there are two techniques to consider for splicing in this case. This is called the fusion splicing. The fusion splicing is a long-term method in which two fibers are fused or welded together. They are fused together or welded together. This method usually results to permanent splicing. Usually result to what we call the permanent splices. The two ends are stripped off of their coating, the protective coating of the two ends of the wire that you want to splice together. You strip them off and they're cut and clipped and then inserted into the splicer. There is a device called the splicer that will help you join them together. There are spaces where you have to put each of the wire so that they can be joined together or welded together to form one wire. Now the ends of the fiber are aligned and the electric arc is fired across the ends. They are aligned and then you fire the electric arc across the ends of the wire, melting the glass and fusing the two ends together. melting the glass and fusing the two ends of the wires together. So this method, I think it's usually, if it's well done, it's a better one, okay, because there will be no air gap between the cores of the two optical fiber cables. Now let's look more intensively into this. There are both manual and automatic fusion splicer. So we can do it either manually or do it automatically. So there are both two methods of doing fusion splicing. One is the automatic method fusion splicing, and the second one is the manual fusion splicing. Is that okay? Now the choice depends on the number of splices that you're going to do. If you have a lot of job to do, it's better to be doing the automatic one. If it's just like few distance or few wires that you do, you can do the manual one. Okay, it depends on the job you go to do, depends on this kind of skills. If you're a technician, you don't know much, then it's better to use the automatic one. If you're very good, you can, and the job is just a little bit, you can, instead of bringing the machine for automatic splicing, then you can just do it yourself. Okay, and of course it depends on the budget, because if you do automatic splicing, you're going to bring a machine which is very, very on the high side. Okay, so typical insertion losses of less than 0.1 decibel frequently in this or in the 0.05 decibel range can be consistently achieved with this. So this is good enough. If you have 0.05 decibel loss rate, insertion loss, or what we call attenuation loss, it's good enough, okay, compared to huge attenuation loss in other cases. Now the second method of splice is called the mechanical splicing. And the mechanical splices can be permanent and also has an economic choice for certain fiber splicing application. Mechanical splices also join two fibers together, but they differ from the fusion splices in that there is what we call air gap existing between the two fibers. Air gap exists between the two fibers. So we have refractive index of the glass interface to air, refractive index of air, and then again back to another glass. So there is refractive index of glass to refractive index of air to refractive index of air, another glass. So there is a glass air glass interface whenever we do mechanical splicing methodology. Is that okay? Are you with me? Okay, good. Now let's move on since you're all with me. Now this result in glass air glass interface. Yes, because in one wire is the glass, the other optical fiber cable is also a glass. So when you do a mechanical splices, there's air gap in between the two. So we have what we call glass air glass interface, causing a severe double change in the index of refraction, or what we call double change in the refractive index. Okay, this change results in an increase in the insertion loss and reflected power. So this change increases what? The insertion loss. Remember, insertion loss means attenuation. So meaning there is greater attenuation in mechanical splicing, and also reflected power that is being reflected in the system. So this is, like I said earlier on, that mechanical splicing has its own disadvantage. However, it also has an advantage because it's permanently and economically convenient for us. Now the conditions can be minimized by what? By using something called the index matching gel. Okay, to minimize these losses happening, the insertion loss, which results to attenuations and reflected power. To minimize these two problems, there's something to mediate the effect of this change. Now, one of that thing is called index matching gel. You have to rub, it's like a gel. Index matching gel is used to rub the joints where you are joining them together. The gel is a jelly-like substance that has an index of refraction or refractive index much closer to the glass. So instead of glass air glass, it's like glass glass glass. So the job of the index matching gel is to improve the interface refraction index, to improve the interface refraction index to something like glass 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 instead of having the glass air glass. Okay, that's the job of the index matching gel. Okay, and once that takes place, then the index change is much less severe now. index change is much less severe, therefore there will be low loss, low insertion loss. There will be no heavy insertion loss. This is an improved mechanical splicing method because you've used index matching gel to improve the surface of refraction to be glass instead of glass air glass. Is that okay? Let's move on. The best method for splicing depends on the application. Okay, well, there is no super best one. It depends on what you want to do, method of application. You can use the fusion splicing method or mechanical splicing method. It depends on the application, which include the expected future bandwidth. What type of bandwidth do you want to have at the end of the day? Is it a gigabit bandwidth? Is it a megabit bandwidth? Okay, depending on which bandwidth you want. Okay, and it also depends on which traffic, what type of traffic you expect, and the job size and the economics of it. Because everything has to do with money. We have to talk about the economics of it. Does it worth it to do mechanical? If it doesn't, even if you're doing mechanical has two types, right? You have the manual one and you have the automatic one. So is it worth it to bring the automatic one? So all of this, you have to look at this before you decide which method you're using. Now let's take a look at fiber connectorization. Let's look at the connectorization method. You know, in fiber connectorization, we use the SC connectors, we use the ST connector, or we use the FC.LC connector, or we use MT -RJ connector, and so on and so forth. The choice of which connector you're going to use in your optical fiber system, these are the edges. These ones are the connectors. We're going to talk about them now. Now, the choice of which one they're different. If you look at that tactically, they're different. They're not exactly the same. The choice of which one you're going to use will be dictated by which hardware you're going to be using on your optical fiber application. Examples are the SC. The SC is this first one, this one, SC connector. The next one is ST, this one. This one is ST connector. Then we have MJ-RJ, this one. This MT-RJ connector, this one. Then we have what we call the LC connector, these two. They are LC connectors. So these are the different connectors that we use with optical fiber. Okay, these are the different connectors we use with optical fiber. And then so at the end, this is almost the end part of our work. But at the end of the day, these are the things we've talked about. We talked about DLD diode laser. We talked about light emitting diode. We talked about distributed feedback laser. We talked about the DWDM, the dense wavelength division multiplexing. Dense wave division multiplexing. Whether you say wave or wavelength is the same, okay? Dense wavelength division multiplexing. Then we talked about VCSCEL, vertical cavity surface emitting diode. This one is same as the tunable laser. Then we talked about fiber, light pipes, glass, isolators, RSC, receive signal power level, and so on and so forth. So then we talk about fusion splicing, mechanical splicing, index matching gel, SC, ST. These are the connectors that are used with optical fiber, the different connectors. SC.ST, we have the FC, we have the LC, we have the MT-RJ connectors. So thank you very much. This is the end of today's section for chapter 3 part 4. Thank you very much. Once again, we invite all of you to continuously learn with us. This is Waidsum University, the fastest growing digital technological university in the world today. Thank you.